Dimensional accuracy is very important in manufacturing. Today, I'm going to show you how to collect dimensional data which is being collected for a component using X-ray computed tomography and how it can be compared back to the original CAD model using Avizo. The CAD model data can be opened up using an STP file, and the X-ray CT data can be opened up as either a TIFF stack or a volume file. To view the CAD model, we can use Display Open Inventor Scene. It's always useful to go through this step to ensure that we have the correct component. To compare a CAD model back to the X-ray CT data, we need to ensure the CAD model has both a surface and a volume. The first step of this is to create a surface for the CAD model itself. This can be done using Open Inventor Scene to Surface. This is a very simple process. We just open up the file and then we click Apply. This then creates the geometry surface label. We'll be using this later on to compare the surface of the X-ray CT data back to the CAD design. But we do need to make sure that the CAD data is aligned with the X-ray CT data. To do this, we need to have a volume. This is achieved by using Scan Surface to Volume. Again, this is a very straightforward process and we should just need to apply. Now that we have a volume for the CAD model, it's useful to display this visually in 3D. And we can compare it back to the surface view to make sure that the two marry up. Because we're going to be opening lots of elements in Avizo, it's always useful to ensure that the project view area is kept nice and tidy. Now that the CAD model has both a surface and a volume, we can now look at registering this to the X-ray CT dataset. The first step I always take is to look at a volume rendering of the X-ray CT dataset and compare it to the CAD model itself. This is to get an idea of how far apart the two volumes are, because I'm going to map these on top of each other. To register them, I'm going to use the option called Register Images. Now the Register Images has been attached to the X-ray CT dataset. I'm now going to have to use a reference, and this will be the Geometry Surface Scan Converted file which I've created above. We can now see that these two volumes are linked. Now registration can take a number of steps. The first step I always take is to align the centres, and we can now see using the volume renderings that the centres have been aligned themselves. The next step will be to align the principal axes. We can now see that the registration has roughly got the two volumes in the same area, or volume I should say. But we need this to be a lot more accurate. To do this, we click on the Apply and we should get a much higher accuracy for the alignment. If this doesn't work very well, then we can always reapply it, but this time using the option ISO Scale. In this example, it produces a much better fit. When the images reappear, we can now manipulate them in 3D space to see how accurately the two volumes have been merged together. Here we can see that there is a discrepancy between the X-ray CT data and the original CAD design. This is where the silver area for the CT data is shown above the actual CAD model. Now that the CAD model and the X-ray CT dataset have been registered, our next step is to measure the difference in the surfaces. The first step is to create a surface for the X-ray CT dataset, and this can be achieved using segmentation. In this example, we used auto thresholding because it gave the most accurate surface profile for the CT data. Auto thresholding will give two outputs. We have the information file and we have the labels themselves. From the labels, we can then create a surface. When generating the surface, it's very important that we do not smooth the surface itself. So we choose the option None. Otherwise, we won't have a true comparison to the actual CAD model. We can view the surface using the surface view, and we can see that the surface is quite rough. And this is very normal for X-ray CT data sets because we're looking at voxels. So there will always be those flat and square edges. We can then use a hidden tool which is called Adjust Sub-Voxel. This can be accessed through the console. To apply Adjusted Sub-Voxel, we need to attach it to the surface data for the CT. We then attach it to the original CT dataset itself. Adjusted Sub-Voxel that will then smooth out the surface by applying the CT surface which we've generated back to the original dataset. The output then can be viewed using the surface view, and we can see that the surface is going to be a lot smoother. To ensure that the adjusted sub-voxel has actually been accurate, we need to actually look at the orthoslices. We can now see that the adjusted sub-voxel gives a more accurate interpretation of what the true surface is compared to the X-ray CT dataset. Now that we're happy with this, we can now move to the next step. The data is now ready to measure the difference in the surfaces between the CAD model and the X-ray CT dataset. To do this, we click on the X-ray CT dataset output, which we've just created, and search for surface distance. For surface distance, we already have the engine part for the CT dataset selected. We now need to link this to the surface for the CAD model. Here we can see that it's applied to the geometry surface, which we created at the very start. For the outputs, we select vectors and distance and click apply. Once the program's finished, we'll get two outputs, the displacements and the distance. We can visualize the difference in the distance map using a surface view. However, this is not very clear by how much the surfaces are actually varying. If we click on the distance now and you apply the surface view, we can see that there are differences between the CAD model and the X-ray CT dataset. But as I showed before, we don't know how much this variation is. So we're going to use an expression which was created by Andreas and Remy at Thermo Fisher, and we can apply this using the arithmetic module. For B, we use the geometry surface. If we use the following expression, the result from the arithmetic module will now give a difference between the surface geometry of the CAD model versus the X-ray CT data. And we can see the values by how much it varies in millimeters shown on the histogram. If we take a step back, we need to have a think about how we represent the differences between the two surfaces. Again, I'm going to use the surface view module, but this time I'm going to use a different color map. We can find different color maps under the options and then go to load color map. Here we're going to choose physics NDT. For the color map, we can then look at the original result for the output. Here we can see that the scales, or the distance, varies from 0.9 of a millimetre below the surface of the CAD model to over 0.5 of a millimetre above it. Next, we need to annotate the colour map. We then apply an appropriate title. In this case, it's very important that we tell the viewer that the measurements are in millimetres. As well as annotating the colour map, it's also important to have an appropriate scale bar. From the current view, it's very easy to see the differences in the distance map for the outside of the component. But there are surfaces which are on the inside, and these are not as easy to view from outside. In this case, we can use an ortho slice to cut the volume so that we can see these inside surfaces and how much they may be varying. The distance map is a very powerful tool for showing the variations between the actual finished component and the intended model. But sometimes we want to add some extra information in. Here I've taken the surface view for the geometry surface and overlaid it on top of the distance map. Here we can clearly see where the finished component is much larger than the intended model. We can then change this to a transparent view so we can see where the finished component is much smaller than the intended model. And here we can see that the colour map marries very well with the differences in the distances for the surfaces. One of the main strengths of X-ray CT data is that you can see hidden features inside of components. And these can also be flaws such as pores or cracks. In this example, we're going to use an ortho slice to see where the pores are inside the 3D printed component and whether these have any effect upon the surface profile. We can see as we skim through the ortho slices that there are some indentations on the curved surface. If we're not careful during segmentation, these small imperfections can actually be mistaken as pores. In this case, it's very important that any segmentation which is carried out as a 3D volume rather than a 2D stack. Here we can see a pore which is very close to the surface. This area here shows a surface imperfection which could be mistaken as a pore if segmentation is not carried out correctly. Once pores and defects have been segmented, it's very useful to visualize them in 3D and see their locations within the object. This will allow us to see if there's a relationship between where the pores are and any surface inconsistencies or variations from the CAD model. Viewing these defects in 3D is also very useful for you to find out whether these are actually near the surface or they're actually within the volume itself of the component. Here I've used the geometry surface view to create a transparent overlay on top of the distance map to view the internal defects.